Okay, so hi, welcome to this next video in linear programming. So in this video, we are finally going to take a look at what the simplex algorithm is doing from a geometric point of view. And we're going to do that in light of the fact that we established from the prior video, which is that when your linear program is in standard equality form, then the basic feasible solutions are the extreme points and vice versa. And so this fact itself was the culmination of many prior videos' results, but they led up to this fact, and now we're going to use this fact to see what's happening with the simplex algorithm. And so intuitively already we have the idea that basic feasible solutions, well, those are the things that the simplex algorithm is iterating over. It goes from basic feasible solution to basic feasible solution, and so correspondingly, that must mean then geometrically it's iterating from extreme point to extreme point. So it's just traveling across various extreme points until it terminates. So that's the idea. So let's see how that works in practice with a specific example. So here's an example linear program that we'll use for this video. And so here on the left-hand side, you can see these are the constraints, and these are all less than or equal to constraints here, and then we also have variable non-negativity, but of course we can write those as less than or equal to constraints as well, just by multiplying by -1. So in a complete sense, these are all less than or equal to constraints, and so it's just intersection of half spaces is geometrically what that is. And so the feasible region is the intersection of all those half spaces. And then on the right-hand side, that's this blue area that we've outlined in blue, that is the feasible region for this linear program. I'll talk about what these green lines are in just a moment. But first, let me just... oh, by the way, you might recognize this shape, this blue feasible region, because we've actually used the same linear program in prior videos. We're using it again in this video. We used it once before, I think. Okay, so, but anyways, so the main difference is that we finally filled in an objective function in this video because, well, the simplex algorithm is trying to find an optimal solution. Well, an optimal solution to what? Well, it's an optimal solution to whatever the objective function is. So we're trying to maximize some objective function. So in order for any of this to be meaningful, we need an objective function. So I've just given an example objective function here that we use. And okay, so first of all, we can geometrically see what the optimal solution is. And so in light blue, I've given the optimal solution. So why is it that this is the optimal solution? Well, it's because of these green lines here. These green lines are the level curves of the objective function. So here's the objective function, and these green lines are the level curves of it. What that means is that, well, we're in two-dimensional space here, right? All the points are coordinates x1, x2, and when you plug those into the objective function, you get some output value. So for this green line at the bottom here, for instance, when you take any point on that green line and you plug it into the objective function, you will get 6 as the output value. So I've labeled this green line with a 6 for the output value that all of these points give you. So for instance, 0, 2 is on that line, and when you plug 0, 2 in, you get 2 times 0 plus 3 times 2 is 6. And but it's not just for that point, it's for any point on this green line. And so it's a level curve in the sense that all the points on this curve, or line in this case, give you the same output value. And but that's just for that line. Now if we move up to this next green line here, we can see that any of the points on this green line, that when you plug them in, they would give you an output value of 9. So that's even better. By output value, I mean the objective function value. And so that's even better than 6. So 6 was not the optimal value because 9 was even better. But actually we can go up even further to this next level curve. We could get 12 for that. So we're doing even better. And so you can see then that, as we're pushing this green line up and up and up, we're getting progressively better and better objective function values. So let's just push it up as high as it can possibly go, and that will give us an optimal value. And so what happens when you push this green line as high as it can go is you get this green line right here. And it intersects the feasible region at exactly one point. It's this extreme point, this light blue point right here. So we can conclude that that is an optimal solution. Because if we took a level curve that was anything below this value of 17 is what it works out to be when you plug it in. but if you took any level curve below this, the optimal value would be strictly less than 17. But of course, we're trying to maximize, so we can do at least as good as 17. But we can't do any better either, because if we move the level curve of this objective function, if we move that level curve up any higher, true, the objective function has increased, but all the points that would lie on that green line, which is even higher up, they don't intersect the feasible region. None of those points are in the feasible region, and so they don't satisfy the linear program. And so the best you can do is the highest level curve you can get that still intersects the feasible region, and that's this green line for the value of 17 that you get when you plug it in, and it intersects the feasible region at exactly this extreme point right here. And so that light blue point, that's how you can geometrically see that this is the optimal solution. So let's see what the simplex algorithm has to say about this. So the optimal solution gives you an output value of 17 at this point in light blue that we had is x star is 1, 5, so 1 over and 5 up. So you can see when you plug in 1, 5 here, you get 2 times 1 plus 3 times 5, and that is 17. And it's unique, by the way. So you can see that it's unique because this best level curve only intersected in one point, and that's right there. So running the simplex algorithm will obtain this unique optimal solution precisely because it's unique. If there were multiple optimal solutions, there could potentially be infinitely many optimal solutions, and then it's maybe a bit ambiguous as to which one the simplex algorithm will end up giving you, at least at a glance. But in this case, we don't even have to worry about that because there's only one solution that we could get as the optimal solution. So this is the optimal solution, this light blue point, and so how will the simplex algorithm work on it? Well, first, note that we're not in standard equality form, so we need to go to standard equality form in order to even run the simplex algorithm. So, I've just rewritten the linear program again, and so we've just called it LP, and there's a correspondence between that, and then the standard equality form version of it. So how do you go to standard equality form when you have a bunch of less than or equal to constraints? You just add a slack variable. That's what you do. So for instance, for this first constraint, 2x1 plus x2 is less than or equal to 10. So what you do is you do 2x1 plus x2, that's what we just had, plus x3. That's a new variable. We call it a slack variable because it just picks up whatever's left over. Because now we want to attain this upper bound of 10 because we need matrix equality constraints. Everything has to be equal to. So we just add a slack variable so that whatever's left over from 2x1 plus x2, there's still some slack to get to 10. So x3 will pick that up so that you can exactly equal 10. And then the same thing for these next two constraints. I've just written the same things, but we've added these new variables, these new slack variables. So x4 for this next constraint and x5 for that last constraint, so that we equal the right-hand sides of 10, 6, and 4, respectively. So those are the matrix equality constraints, and then these are also, you can write them as less than or equal to constraints, but since they're already variable non-negativity constraints, just keep them like that, because for standard equality form, it requires that all the variables are non-negative. So here's x1 and x2 again, and then also for these 3, 4, and 5 variables, they're also non-negative, simply because that's the constraint that we need to be in standard equality form. And of course that works, by the way, because originally this was less than or equal to 10. So when you have to add on something non-negative to equal 10, that would just make sense anyways. So anyways, this is all consistent, and this is the standard equality form of the original linear program. And the idea is that they're equivalent linear programs in the sense that that it's true that there are more variables here, but these variables, for any 5 tuple, x1, x2, x3, x4, x5, that's just a point in space, and that point in space bijectively corresponds to a coordinate pair x1, x2, just in the two-dimensional space that we were originally working with. So there's a bijection there, and those bijective correspondences, when you plug them into the objective function, it's the same objective function, so it's the same objective values. So yeah, this is just a reformatting. Well, it's it's just it's a different linear program, but it's equivalent to the original one, in the sense that there's a bijective correspondence that gives you the same objective function values. So what is the bijection just explicitly, even though it's kind of clear what it should be? So if I take a point x, which is x1, x2, and I'm going to travel to we'll map it to x hat, just so it doesn't, it's not ambiguous what the x is. So x is just x1, x2. X hat will be all 5 coordinate points. So it's the first 2 points, x1, x2, and then there's x3, 4, and 5 as well. But we know what they have to be. Once we've decided what x1 and x2 are, then x3, x4, and x5, those are just the variables that pick up the slack. So whatever the slack was left over from 2x1 plus x2, you know what these things have to be. So you could, or in other words, you can solve for x3, x4, x5 in terms of x1 and x2. And so that's just what we've done here. We've just solved for x3, 4, and 5 in terms of the constraints, in terms of x1 and x2. And so that's how you go from a point in x1, x2 to the corresponding point in, with 5 variables. And then if I'm starting at a point in 5 dimensions, then to go to the 2-dimensional corresponding point, it's just those first 2 points. It's just the first 2 coordinates, x1, x2. So it's just a projection down on the first 2 coordinate pairs there, coordinate points. So this bijection, this is just saying that x is feasible for the x being the x1, x2, just the 2-dimensional variable x, is feasible for the original linear program if and only if this x hat corresponding point is feasible for the standard equality form version of the linear program. So we have that bijective correspondence, and then also there's an extreme point correspondence. That is, x, if x is between x prime and y prime, so that it's not strict. That it's not an extreme point if it's between 2 other points in the polyhedron, so that it's not an extreme point. It lies on that line segment in between. Then what you do is you just map x prime, y prime, and x. Just map those under that map that we just established into the corresponding 5-dimensional coordinates. So x prime hat, y prime hat, and x hat. So if x originally lied between x prime and y prime, then the corresponding x hat will also lie between x prime hat and y prime hat, and then vice versa as well. If you started with this point, you can just use the map that we went in the other direction. You just project back down into 2-dimensional space, and if this point was not extreme, then the corresponding projected point is also not extreme. And you can verify that algebraically just by using, by definition, what it means to not be extreme. That means that x can be written as strictly lying in between the line segment of x prime and y prime, and correspondingly, then if you look at the map, what that means, what is lambda x prime plus 1 minus lambda y prime, use the map that we just established, this map right here, and you'll see that x hat is strictly between x prime hat and y prime hat, and then vice versa. And so anyways, the whole point of that is just to say that x is extreme if and only if x hat is extreme. So the extreme points of the feasible region for the original polyhedron that we had, they map bijectively with extreme points of the standard equality form version of the linear program. So everything really is equivalent in that sense. So yeah, so just to recap, if x is feasible for the original linear program, then x hat is feasible for the standard equality version, and vice versa. And then if x is an extreme point, then x hat is also an extreme point for the standard equality version, and vice versa. So the feasible points are in bijective correspondence, as are in particular the extreme points. So what does that mean then? Well, you always run the simplex algorithm on standard equality form version of a linear program. So do that, run the simplex algorithm, and then what we know is that we have a basic feasible solution at each iteration of this standard equality version of this linear program. But But we now know from this prior video that basic feasible solutions are extreme points. So we're at an extreme point of each of the polyhedron associated to the SEF version of the linear program. But what we also just established in this fact 2 here is that an extreme point for the linear program of standard equality version is bijectively corresponding to an extreme point of the original linear program. So that means then that basic feasible solutions for the standard equality version, those are extreme points of the standard equality version, which are extreme points of the original linear program. So yeah, so basic feasible solutions are corresponding to extreme points of our original linear program. And so I won't actually run the simplex algorithm, but if you want, you can, but this is what happens when you do that. You start at this basis here, and then you'll go through multiple iterations, and so your first basis, remember the simplex algorithm is going through various bases of your linear program. So first basis, so there's in the standard equality form version of our linear program, there's 5 variables, right? There's the original 2 plus the 3 slack variables, so there's 5 overall. So then there's 5 indices that we're pulling from to form our bases. So 3, 4, and 5 is the first basis, and then the basic feasible solution for that basis is this x hat. It's the 5 coordinate points 0, 0, 10, 6, 4, and then correspondingly the bijection between these is that you just project down from this 5-dimensional point to this 2-dimensional point, just looking at the first 2 components. It's 0, 0. So it's those are the quotes real variables. The rest of these components were slack, right? So the original 2 are the 2 coordinate points that we're concerned with, 0, 0. So this is for x for the original. By the way, I've just written transpose because we're writing these as rows right now, whereas vectors are typically considered to be columns, but just rows for more compactness. But okay, and then you iterate through the bases, and that's going to iterate through these various basic feasible solutions, and then correspondingly, that's iterating through these extreme points of the original linear program. So what does that look like? It looks like this. So we start at 0, 0, and then we go to 5, 0, 4, 2, and 1, 5. So that was right here, 0, 0, 5, 0, 4, 2, 1, 5. And so this is the original linear program, and these are the points that it iterates between. And we just said that, so we started with basic feasible solutions of the standard equality form version, and those corresponded to extreme points of the standard equality form version, which in turn corresponded to extreme points of the original linear program. So here's extreme points of the original linear program that our simplex algorithm is iterating from. So here's what the simplex algorithm is doing. It starts from this extreme point, and then it goes to this extreme point, 5, 0, and then it goes to this next extreme point, which is 4, 2. I know it doesn't look like 4, 2, but it is. And then it goes to this final extreme point, 1, 5. And that, remember, is the optimal solution that we said was the optimal solution in the start. So we already knew that was going to happen, and then simplex algorithm confirms it, and it arrives at that solution in this manner. It starts at this extreme point, then it iterates to there, then to there, and then to there. And so that's the traversal that geometrically the simplex algorithm is making. So yeah, so we get this final fact that we've said, but here it is in writing. Simplex algorithm, it iterates from extreme point to extreme point, and that is how it works. And so these are actually the extreme points of the original linear program, not even in standard equality form, but the point is that as long as you have those the appropriate correspondence, then you just go to the standard equality form version, and the extreme points are in bijection. So this is kind of general in that way. So so that's really the insight that we wanted to develop in this video. So when you're thinking of what the simplex algorithm is doing, think of this. Think of some corner points, or in other words, extreme points, and simplex is just maneuvering around a whole bunch of them until it finally arrives at some final destination, or it determines that your linear program is unbounded. Then one of those two things will be what happens. So that's geometrically what the simplex algorithm is doing. So there's maybe a few more things to conclude that we can wrap up with, but I'll save those for a subsequent video. And then there's more topics in linear programming that can be talked about beyond the simplex algorithm. So anyways, that's it for this video. So thanks for watching.